Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Sol Gel Technique from paper Nanoscience and Nanotechnology. So students, let us first see what we are going to learn in this module. Firstly, in this module, Sol-Gel technique is explained and the various stages in processing are discussed. Then, the various types of gel and the classification is studied in this module. Further, precursors which are used in sol-gel processing are described, and hydrolysis, condensation, activation, and polycondensation are explained in this module. Further, the process of gelation is explained, and the effect of zeta potential on gelation is discussed. Sol-gel is broadly defined as the production of the solid materials like metallic oxides from the solution state reactants or precursors, that is, the starting materials. The precursors usually are metal alkoxides which cross-link forming metal oxane gels or metal iron chelate complex or metal containing organic polymeric gels. The composition and structure of end product is strongly affected by the choice of precursor. Sol gel processing or sol gel chemistry, as it is often termed, can be used for producing solid material from chemically homogeneous precursor. By exploiting the arbitrariness involved in solution state, it ensures atomic level mixing of reagents, and therefore it can form complicate inorganic materials at low temperatures in short processing times. Moreover, sol-gel chemistry also enables better control over the particle size and morphology. In this module, the participants will learn the basics of sol-gel technique for nanomaterial synthesis. In a conventional sol-gel method, precursor goes through reactions of hydrolysis and polymerization to produce a colloidal suspension, or we can say a sol. Complete polymerization along with subsequent loss of solvent directs conversion from sol, that is liquid phase, to gel, which is in solid phase. Films are shaped on the substrate either by dip or spin coating techniques. A wet gel is formed once the sol is casted into a pattern. Further drying and sintering convert the wet gel to dense ceramic. An extremely porous and very low density material termed as aerogel can be formed by removal of solvent from the wet gel at some supercritical conditions. Homogeneous and ultra-fine ceramic powder can be produced by employing spray pyrolysis, precipitation, or emulsion techniques. We next elaborate the various stages in the sol-gel processing. First one is the sol. The colloidal suspension of very tiny solid particles within a continuous liquid medium where only Brownian motion keeps the particles suspended is termed as soul. Sols are highly stable and demonstrate Tyndall effect. Example, blood, paint, etc. Solvent processing involves producing inorganic polymers and ceramics from solution, where the liquid precursors are transformed into a sol and then eventually into a networked structure which is termed as gel. Conventionally, the sol is prepared via hydrolysis and condensation of metal alkoxide precursors. Figure 1a shows the steps which are included in sol-gel technique of nanoparticle synthesis, and figure 1b indicates the temperature which are involved at each step. So, we can see in figure 1a that the precursor it dissolves to form the sol. The sol can be stripped or dipped and caked to produce thin films, or it can be used to form the powders. If the sol is dehydrated in a reaction, then it will form the gel. The gel on rapid drying will get converted into aerogel, or if we add the surfactant organic suspension, then it gets converted to zero gel, which can form dense ceramics. In figure 1b, we can show firstly the sol is produced at relatively low temperatures of 200 to 400 degrees centigrade. Then after some time the gel is formed. Then this is known as basically the gelation process. Then the gel is aged for a certain amount of time. Then it is dried at almost the same temperatures. Then the next step is the stabilization, which takes place at high temperatures of around 600 degrees centigrade, which forms the porous gel. The next step is the densification, which undergoes at high temperatures of 1100 degrees centigrade, where a dense gel is produced. We next discuss the various types of gel. A gel can be produced in several different ways in sol-gel technique, such that slight variations in the processing conditions may yield gels having remarkably different structures. Gel is typically described as a non-fluid three-dimensional network which is surrounded by a liquid phase. There have been numerous attempts at classifying gels. One such effort was undertaken in 1974 by Flory, who divided gels in four types. These were first ordered lamellar gels, including glaze or surfactant mesophases. Then covalently networked polymers. Next is physically clustered polymer networks such as hydrogels, which are created by helical junctions. And lastly, the disordered particulate gels. Nonetheless, for preparing inorganic solids via sol-gel processing, another more robust distinction was proposed in 1996 by Kakihana. The details are given in the next slide. Based on this classification, the various types of gels used in sol-gel technique are classified as colloidal, the metal oxane polymer, metal complex, polymer complex 1, and the polymer complex 2. Now for the colloidal gel, the bonding is that the particles are connected by van der Waals or hydrogen bonds. The source is a metal oxide or hydroxide salts. The schematic is also shown in the table. For the metal oxane polymer, inorganic polymers are interconnected by covalent or intermolecular bonding. Here the source is the hydrolysis and condensation of metal alkoxides, which is shown in the schematic. For the metal complex, they are weakly interconnected metal complexes. The source is the connected metal complex solution, which forms resins or glasses and can be seen in the figure. Then the polymer complex 1 is the type of gel where in situ polymerizable complex is formed. This is also known as Pechiny method. Here the bonding is the organic polymers which are interconnected by covalent and coordinate bonds. Here the source is the polyesterification between polyhydroxy alcohol and carboxylic acid with metal complex. Then the polymer complex 2, here the coordinating and cross-linking polymers forms the gel. The organic polymers are interconnected by coordinate and intermolecular bonding. The source is the coordinating polymer and metal salt solution. Apart from precursor synthesis, the sol-gel technique can be summarized as firstly, synthesizing salt via hydrolysis and partial condensation of precursors. Secondly, producing gel via polycondensation. The next step is the aging, then the drying of the gel to produce zero-gel or aerogels. Then removing the MOH groups present on surface by heat treatment at elevated temperatures. Let us study the origin of sol-gel processing. Sol-gel process was observed for the first time in the 19th century when a silicon-based alkoxide began to produce a gel upon contact with air. Extensive investigations lead to the discovery of the fact that this process was driven by the moisture present in air, which first hydrolyzed the silicon alkoxide and then condensed it. Since then, both these phenomena have been subject of numerous studies, resulting in development of several variants of these processes. These processes can now be tuned by catalysis with acid or base, thereby producing gels of rather different structures. Presently, salt gel processing is the most frequently used technique in materials chemistry. Let us study about precursors. Precursors are the starting materials which are used to prepare the desired products. The earliest precursors used in salt gel processing were the metal alkoxides. Metal alkoxides were hydrolyzed and they were condensed to prepare sol and then gel. However, hydrated metal species can also undergo hydrolysis and condensation. The most popular alkoxide-based precursors include some transition group elements such as titanium, zirconium, and p-block elements such as aluminum, silicon. Metal oxide, alkoxides preparation depends on the type of metal and can be prepared in many ways. Analogous to the original mechanism, alkoxides can be prepared by treating metal chlorides with alcohols. Highly reducing metals such as alkali metals and lanthanides readily react with alcohols to form corresponding alkoxides. Another method to produce metal alkoxides is anodic dissolution of metals in alcohols along with an electroconductive additive, for example, lithium bromide. Similar to monometal alkoxides, bi and trimetallic alkoxides have also been synthesized. The suitability of the various alkoxides as well as the product of reactions depends upon many parameters. One such factor is how electronegativity differences between the oxygen and metal influence the ionic nature of metal oxide bonds. This is determined by using the partial charge model. Second such factor is the alkyl or aryl chain's capacity to donate or withdraw electrons on the stability of the alkoxy groups. These two parameters affect the relative rate of hydrolysis and condensation, and therefore the intent of oligomerization or polymerization, eventually affecting the gel structure. We next discuss the hydrolysis and condensation process. Hydrolysis and condensation strongly depend upon the process parameters, that is, the nature of the R group, water to alkoxide ratio, and the presence and concentration of catalyst. Hydrolysis and partial condensation of precursors like inorganic salt or a metal or alkoxide solution result in the formation of soap. Gel is formed by the extended condensation of the soil particles to create a 3D network. Gel is a diphasic material wherein solid phase encapsulates the solvent or liquid phase. The molecular weight of the resulting oxide species constantly rises. To remove the encapsulated liquid from the gel, either the evaporative drying or supercritical drying or extraction are performed. The resultant solid products are termed as xerogel, which is produced from evaporative drying, and aerogel, which is produced from supercritical drying respectively. The aerogels are highly porous and have very large pore volumes. The differences between salt gel technique and other solution-based techniques, example precipitation and crystallization for producing materials are: first, clear colloidal suspension is produced in salt gel processing by the partial condensation of dissolved molecular precursors. Then, during gelation stage, these colloidal particles aggregate to form polymeric chains by chemical bonding between local reactive groups present at the surfaces. Both these steps are determined by the condensation processing, whose first step involves the hydrolysis of hydrated metal ions or metal alkoxide molecules. The reactions involved in this case are olation, oxidation reactions between hydroxylated species. Olation is the condensation reaction wherein two metal centers are bridged by hydroxyl bonds, that is OH, whereas in oxidation, an oxo bridge O is formed between two metal centers. We next discuss the activation and polycondensation. Metal alkoxides are the most extensively used precursor materials in solvent chemistry owing to their commercial availability in extremely pure states, and also their solution chemistry is well understood. For producing alumina and zirconia salts, aluminum propoxide and zirconium propoxide are employed as respective precursors. The hydrolysis of metal alkoxides is carried out in alcohol solution having a desired amount of water. The general forms of hydrolysis and condensation processes can be described as hydrolysis is MOR plus H2O gives MOH plus ROH. The condensation process is MOH plus XOM gives MON plus XOH. Here, N is a metal and X is H or R, that is an alkyl group. These equations present a very simple picture of the solvent chemistry without elaborating upon the intermediate or end products. Nonetheless, these equations provide a general idea of the formation of three-dimensional gel network, which is driven by the hydrolysis and extended condensation. Let us next discuss the factors influencing any of these reactions. Factors that influence any of these reactions also influence the properties of final products. The most crucial factors are amount and rate of water addition, and secondly, the solution pH. The amount of water added can be described in terms of hydrolysis ratio H and written as H is equal to water in mole divided by metal alkoxide M over M in moles. When H is less than 1, few MOH are available for cross-linking and gelation, and thus there is less possibility of forming an infinite network. When more water is present, that is, H is greater than M, a highly cross-linked gel forms. For a fixed amount of water, the process can be controlled by controlling the rate of water addition. The relative rate of hydrolysis and condensation processes is also affected by the pH of solution. For pH less than 7, hydrolysis rate is faster than the condensation rate, leading to the formation of a poorly cross-linked gel. When pH is greater than 7, condensation rate is faster than the hydrolysis rate, resulting in the formation of highly cross-linked gel that contains colloidal aggregates. Let us now discuss about the gelation. Gelation